Kurt. I've been talking about all these really hard things. And I've been talking about them on YouTube mostly because I don't want to write academic papers. And now I've come to the conclusion that I'm still talking in academic only over YouTube. So it's even more difficult to understand because the academics aren't going to listen to me. And no one in real life is going to listen to me. So really, I'm talking to audience of zero. And I'm trying to explain what I'm trying to explain in a somewhat easier to understand language tonight. And we'll see how it goes because I still think it's going to be hard to understand if you haven't been introduced to these topics before. But I used to teach an introduction to comp sci class just for situations like this to explain computer science and what I do to the lay person. Not that you're not special, just not in the field of computer science, maybe. This is for people who aren't special in the field of computer science. I'm not special in the field of computer science if you're talking about software engineering. I'm special in the field of computer science for the theory which applies to software engineering. In fact, all of software engineering is based on that. But anyway, I'm getting better at writing software. It's just I have a slight learning curve. Anyway, not the purpose of this. I'm saying I know what it is to be incompetent, and it's not a bad thing. It just recognizing that you don't understand something is the first step to understanding it. Blowing shit up in your face is how you figure out how to not blow shit up in your face. You don't do it again. I blow lots of shit up in my face all the time, so I don't know what I'm talking about. It seems like half of everything that I do is wrong. But not this, hopefully. Anyway, a great way to psych yourself up before trying to explain something that no one believes you on, Kurt. It's fine. So let's go into what cryptography is first. And cryptography, if you don't know, is related to crypto. And that crypto, money, Bitcoin, uses cryptography in order to run the infrastructure in which you're going through all these transactions and you're signing them and verifying them in a special way so you know that all the transactions are valid without having basically an overlooker that's sitting there and saying, or like a bank that's sitting there and saying, yes, this is a valid transaction. Instead, you're letting the computer determine its validity itself. And that's why if you break crypto, you're kind of breaking that trust that you have with your computer. I mean, cryptography. I'm going to use crypto for cryptography now, and that means the field of cryptography in computer science. So if I say crypto, I mean cryptography. From here on out, I'm not talking about the money. Crypto or cryptography is this field that studies these functions in which they're easy to compute one way, but you can't compute it back. And it's important because if you have a function that you can go one way and not the other, then you basically have a key, right? Because on the function that you can go that way, you call the key that you have the private key, and then you're going to plug it into the function, and it's going to spit out the public key that you can show to everyone and their brother. It doesn't matter, the public key, because you know no matter how hard they try, it's going to be really hard for them to convert the public key back to the private key, because you have these functions that are really easy to go one way, but really hard the other way. And that's basically what cryptography is. And now let's go into P and NP, these complexity classes in the realm of the gods that no one understands what Kurt's talking about. He's saying that they're equal. If I look up what P and NP is on Google, everyone's saying they're not equal. What the fuck is Kurt talking about? But these complexity classes are such that NP are problems that you can verify in polynomial time. It's easy to go that way, to verify it, that you have the right answer, but you can't determine them in polynomial time. And the inverse function, that's really hard, seems to be an NP, right? Because in poly time, given the right answer to the inverse function, I can compute the inverse, but I can't determine what the private key. Like, if I have the private key, I can determine that it's the right private key by plugging it into the first function. But if I don't have the private key, no matter how hard I try, I can't take the public key and determine the private key. So it seems like these problems are in NP, right? And that's why we say that cryptographic hashes are in NP, because we have to be able to verify them in polynomial time. Otherwise, computers aren't going to be able to do their transactions. Basically, this is how computers do handshakes between each other. So if I'm trying to connect to Google, I'm going to touch Google, and Google's going to come back with something saying, hey, I'm Google, basically verifying that I've hit the right place instead of somebody that's posing as Google. And that's what HTTPS is versus HTTP. If you see that in your browser, if it says this is not secure, it's because you're hitting that and they aren't doing any handshake with you in order to verify that they are themselves and who they say they are. So if you ever see that in your browser, this is not secure, it's because you're HTTP and someone could not secure. Hypertext protocol. We use acronyms in computation or computer science because we don't know what the fuck we're talking about. Anyway, HTTPS is the secure version. So basically, if you have a non-secure, you just are hitting a server, and it could be anyone because they haven't done that handshake with you. That's all it's saying. That's all it's doing. So it's like little things like that. Computers interacting. You could take this same thing and saying, like, how do we authenticate against computers? We have, like, CAPTCHAs. When you click the things, I am not a robot. So this is an automated authentication where you don't need a human proxy. Just the computers can take care of it. Now, when you're authenticating against computers, you will sometimes use an SSH key. If you've ever taken computer classes, and that's the same thing. You're authenticating via cryptographic hashes at that point. So that's the whole thing. And now people are really concerned if P equals NP, because then I can determine these really hard problems in polynomial time based on input. So that's why they're freaking out, because they see it as a verifier versus a determiner. And if I can determine the answer in polynomial time, all hell breaks loose. I'm not going to be able to have handshakes between computers. How am I going to have this? How am I going to continue to automate the world without having a human proxy in between? I mean, think about all the transactions that happen automated on your credit cards, on anything that don't require human input. Our entire world is automated and depends on this. So when I say that P equals NP, people are just laughing at me because they're like, no, no, that's not true. We need P to not equal NP. So I understand. And in my 2 videos ago, I said that cryptography is probably not going to break, even though that P equals NP. And now, in the last 5 minutes that I have, I kind of want to explain why. So, first of all, these cryptographic hashes are very hard, are not. So there's already rainbow tables for cryptographic hashes. There's already rainbow tables for, like, clear text passwords, and then encrypted passwords, so that people have already tried to do this with cryptography. Store the answer to the what the private key should be and its associated public key. So if I get the public key, I now know the private key. So people have already tried this. There's already rainbow tables of MD5 hashes everywhere. If you store 3SAT, or 3SAT's my favorite one, it's an NP complete problem. And I don't know if I've said this already in this lecture. I've tried to do this lecture a couple times. So NP complete problems, I don't think I've explained this. NP complete problems are such that in polytime, there's a function that can convert all problems in NP into 3SAT. So basically, I can, in polytime, based on input length, convert these hashes, these public keys, into a instance of 3SAT in polytime, and then solve the 3SAT and convert it back into the private key and return it. So that's why NP complete problems, why you want to store all the answers to NP complete problems so that you can query it. It takes time to convert, and it takes time to store the algorithms to convert hard cryptographic hashes to 3SAT. It also takes time to store all the answers to 3SAT in a database. It takes a hell of a lot of space to store all the answers to 3SAT in a database, probably more space than is currently available. And it also takes time just to construct that table. Like, who's going to construct it? Is it going to be a computer? Is it going to be human? Who's going to solve the answers to 3SAT and put them in a table? But once you do it, you don't have to do it again. You can query that table and always have the answers. And then you just convert and then solve. 3SAT is Boolean. It's Boolean such that you have term 1, term 2, and term 3 ORed together. So T1 or T2 or T3, and then that's a clause, and then you have and then a bunch of other clauses. And then 3SAT asks, is there assignment to these terms such that the whole expression comes out true? That's what 3SAT is, and it is NP complete. So if you store all the answers to 3SAT in a rainbow table, you can query that, convert your really hard problems, query the rainbow table in polytime, and then convert it back, and you have the answer to your really hard problems. Like I said, I converted the math, how much space you would need the other day, just to brute force store every single input string for 3SAT, and I explain how you can kind of equate input strings in order to pare that down and ensure that you only have a transition table of a certain size for each string with a max term length of a given size. I put terms in between ors and clauses in between ands. That's how I say it. But if you know about computational complexity, you want to see the maths there. I tried to compute them out. No saying if they're perfect. However, I do think that you could take what I put up the other day and bring the space down by sacrificing time, because if you only have to store some of the answers to the 3SAT problems, and you have some sort of algorithm that takes all inputs and converts it to a master key that you know is in the database, and then just queries on that master key, and it does that deterministically on all inputs. There's a mapping. then you only have to store so many master keys instead of all the answers. Now, finding that master key algorithm and sacrificing time and space for that, that's something that a mathematician should do. That's not me. But those are I hope I tried to explain.